Hello and welcome. My name is Ingrid Donnelly, Product Manager with IEEE Educational Activities. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Our virtual event today is the IEEE Guide to Autonomous Vehicle Technology. This live webinar will give you an overview of the course program, also titled IEEE Guide to Autonomous Vehicle Technology, which is now available. If you would like to tweet about the event today, please use the hashtag IEEELearn. Before we begin, should you need any technical assistance during the presentation, either click the yellow question mark at the bottom of your screen or type your question in the Q&A section. If you have questions about the topic during the presentation, please use the same Q&A section. We will get to as many questions as time allows. However, please know we will be compiling unanswered questions and providing responses via email at a later date. Please know an IEEE Certificate of Participation is available to all attendees. Click the certificate icon at the bottom of your screen to access. Today's presenters are Dr. Alex Wiglinski, President of IEEE Vehicular Technology Society, Dr. Naxer Lashgarian Azad of the Systems Design Engineering Department at the University of Waterloo in Canada, and Dr. Steve Bozar, CTO and co-founder of May Mobility. At this time, I'd like to hand it over to Dr. Alex Wiglinski.
Hello and welcome, everyone. My name is Alexander Wiglinski, President of the IEEE Vehicular Technology Society, one of the two supporters or sponsors of this very exciting series of e-learning modules on autonomous vehicle technology. This has been an exciting project over the past 2 years in order to provide a collection of very insightful lectures and materials on this cutting-edge technology that is affecting all of society. The Vehicular Technology Society, in cooperation with the IEEE Educational Activities, have worked over these past 2 years in order to bring together six world-renowned experts in various aspects of autonomous vehicle technology in order to provide and produce these lectures, 7 lectures, on various elements that are kind of core to every autonomous vehicle platform. So before going into a description of the overall series of lectures that form this Guide to Autonomous Vehicle Technology, I'm going to take a few minutes and describe what is IEEE VTS, one of the sponsors of this guide. So IEEE VTS is a technical society within the IEEE. It consists of approximately 5,000 members worldwide who are interested in all elements and aspects of vehicular technology, whether it be land transportation systems, such as electric railway platforms and systems, motor vehicles, which involve everything from the electric components, platforms that drive vehicles, all the way to the powertrain and propulsion of these platforms, and mobile radio, such as 5G and wireless connectivity, MIMO systems, and cognitive radio. So all of these elements form the critical sort of key ingredients to any sort of vehicular platform out there. And our society not only focuses on the theoretical knowledge that enable us to explore and advance the current state of the art in vehicular technology, but also focus on the applied. How do we translate that theory into reality? So with our approximately 5,100 members worldwide, our goal is to provide services events and activities that help promote the professional development and growth of our members, as well as provide knowledge and networking opportunities for our technical community worldwide. And this is achieved through a number of activities and services and events, including conferences such as our flagship conference, the Vehicular Technology Conference, or VTC, as well as the Vehicular Power and Propulsion Conference, or VPPC, and the Joint Rail Conference, which we are a proud co-sponsor of. We have a number of high-quality, high-impact publications, peer-reviewed publications, including our Transactions on Vehicular Technology and the Vehicular Technology magazine. We are very active in standards, such as connected vehicles and a number of other activities in railway systems. We also reach out to our members worldwide through our local chapters. We have over 50 of them, and these are great ways of engaging with our membership around the world and enable them to learn about the latest in vehicular technology, as well as network with each other, and as well as try and advance their professional development and growth. We have an online VTS resource center that allows for our members, as well as the technical community in general, to access online educational resources to learn more about the latest and greatest in vehicular technology. We've got a collection of workshops, summer schools, and other initiatives that really provide our members and the technical community with the cutting edge in vehicle technology, whether it is in land transportation, motor vehicles, or mobile radio. To learn more, please visit our website at vtsociety.org, as well as find us on Twitter, Facebook, and LinkedIn. To give a little bit of a sort of a preview of some of the many activities that the VTS is involved in addition to this seven lecture e-learning series in autonomous vehicles, several other autonomous vehicle related events and activities that the VTS is very active in and supporting include our special issue on connected and autonomous vehicles in our Transactions on Vehicular Technology. The manuscripts are due on September 1st, 2019, and more information can be found at the URL listed in the slide. We also have the second edition of our Connected and Autonomous Vehicle Symposium that's being held in Honolulu, Hawaii on the 22nd and 23rd of September 2019. Again, more information can be found at the URL listed on this slide. Finally, we're very excited about the launch of the first ever IEEE workshop on situational awareness for emerging network-enabled transportation systems, or SafeNets. And this event is being held on October 1st, 2019 in Lowell, Massachusetts, just slightly outside of Boston. And to find out more about this event, as well as register, please visit safenets.org. And as usual, keep track of all our activities, events, and services through our society website at vtsociety.org. So, why do we care about autonomous vehicles? Obviously, there's been a lot of hype on the media about self-driving cars and other sort of platforms that can drive with little to no intervention by a human operator. Well, there are many different but related reasons why we should care about it. Why should we care about autonomous vehicles? How will it change society? And those include things like safety, for human occupants and drivers and passengers on our roads today. The economic benefits of having self-driving platforms on our roads. Green, convenience, social benefits, even enhancing mobility for folks who might not otherwise be able to travel on roads and streets across our country and around the world. So we really need to look at how we can advance the current state of the art in autonomous vehicle technology in order to really support this deployment, to make it reliable, to make it safe, in order to really capitalize on the rewards that can provide all of us, and really provide that increased safety, that increased greenness and sustainability, that enhanced mobility benefits that we all think about and dream of, to make it a reality. So this e-learning a series of e-learning modules is really important because it helps try and provide our community with sort of the latest knowledge in terms of understanding techniques and technologies in terms of how autonomous vehicles work, as well as where we can make further enhancements and take them to the next level to ultimately reach that reality of the benefits that we described on this slide. So in order to understand what it means to be an autonomous vehicle, not all autonomous vehicles are either autonomous or not autonomous. There's shades of gray, if you will, of autonomy. So the Society of Automotive Engineers, or SAE, came up with a number of levels that describe how autonomous would your vehicle be. Everything from level 0, which is no automation whatsoever, which means your hands are always on the steering wheel, and that human operator is constantly making all the decisions by him or herself without any sort of automatic features by the vehicle. And it goes all the way to full automation, level 5, where the vehicle is completely capable of operating itself across a variety of situations and circumstances without any intervention by a human operator. And then, of course, there's the shades of gray that I was mentioning about, levels 1 through 4. And as you progressively go through those levels, the challenges of implementing that level of automation becomes quite a bit more substantial, right? So your vehicle needs to make decisions on the fly. It needs to take account of information in the surrounding environment. It needs to adapt to sort of the time-varying conditions of the road, the weather, maybe the traffic conditions, going from like no rush hour to bumper-to-bumper traffic, if you will. So knowing these levels of autonomy, we now need to look at what do we need in an autonomous vehicle in order to perform at one of these levels. So let's go to the anatomy of an autonomous vehicle. So if we take apart an autonomous vehicle, and here's an example from a company called Waymo that is a spin-off from Google that allows for autonomous driving in this platform. And what you will see here is this vehicle probably has sensors, whether it's LiDAR, right? So it's a form of a laser sensor that is able to sort of detect objects at specific distances and create a point cloud in order to really allow the vehicle to visualize what are the obstacles physically around it. Radar, which we all know, but that's a critical component of a lot of autonomous vehicle platforms, and even camera and vision systems. There's also discussion about connectivity, such as DSRC, dedicated short-range communications, cellular, and GPS navigation, in order to help guide that vehicle, as well as communicate potentially with roadside and other vehicle platforms on the road. Control and actuation, such as autonomous steering and braking, will be critical elements of any autonomous platform. And one thing that folks need to look at more and more is human factors. How does the human interact with the autonomous platform? And that brings up the area of human-computer interaction. Obviously, a critical component of any autonomous vehicle is its ability to compute, to take all that data and process it in order to come up with actions that can then be fed back to the platform's actuation and control systems in order to drive safely on the road. So things like field programmable gate arrays, graphic processing units, microprocessor systems are all critical computing technologies that are probably deployed in a lot of these autonomous platforms. And of course, software. Like no autonomous vehicle would be complete unless there was extensive software in order to really implement all those actions. So how does this e-learning series touch upon these topics? Well, course 1, right, and I'll explain what these courses are. In this e-learning series, we have 2 courses that focus on sensing technologies. Right, actually 3, my apologies. Courses 2 and 3, which I'll describe in a second. And courses 5. Connectivity is covered by course 7. Control and actuation is covered by courses 1 and 6. And then finally, very importantly, an excellent lecture on human factors is course 4. So these courses, and we're really excited to have with us 2 of the subject matter experts that have presented these lectures in this e-learning series. These are the world-renowned experts in each of these individual areas. For instance, Course 1 is presented by Professor Yue Wang from Clemson University, and her work in control and connected autonomous vehicles. And she'll really go into the detailed control theory of how these platforms work. We have 2 lectures by Professor Fabien Moutade from École Nationale Supérieure de Mines de Paris, and he'll talk about visual detection and recognition using vision systems for these autonomous platforms. We have a human factors lecture by Professor Shan Bao from University of Michigan Dearborn. And with us today, we're really, really excited to have with us Dr. Steve Vozar from May Mobility, who's going to be talking about sensors in autonomous vehicle systems. And it's really exciting because May Mobility produces these autonomous vehicle platforms. So it's not only a theory, but also the implementation of these sensing systems on autonomous vehicles that he'll discuss a bit about. Also with us on this webinar is Professor Nasser Lashkarian Azad from University of Waterloo in Waterloo, Canada, and his work into the development and, very importantly, the validation of these intelligent vehicular platforms and their control. Finally, to round out our these 7 lectures is Mr. Sunzuki Aoki from Carnegie Mellon University, and his lectures on the cooperation of these autonomous vehicles that include the connectivity aspect. So with that, I'm going to very happily turn over the mic to Professor Nasser Lashkarian Azad, and he'll discuss a little bit about his lecture and his work into the validation and development of intelligent vehicular control systems.
Thank you, Dr. Wiklinski. Hello, everybody. My name is Nasser Lashkarian Azad, an associate professor in the Department of Systems Design Engineering at the University of Waterloo in Canada. Thanks for attending this webinar, which is dedicated to introduce the IEEE Autonomous Vehicles courses. I have worked with Dr. Alex Wiklinski and his colleagues to develop a module of these courses called Developing and Validating Control Systems for Connected and Automated Vehicles, or CAVs. In this presentation, I would like to give you an idea about the contents of this specific module. As you are probably aware, recently there has been a lot of efforts in the area of automated vehicles, AVs and CAVs, especially to develop decision-making and control systems with optimal performance for these vehicles. However, developing reliable technologies for this purpose, which are practically applicable to all real-world driving conditions, is still challenging. This is a very difficult control problem, particularly due to uncertainties like road condition variation and onboard sensing defects and flaws, such as radar or LiDAR's object detection errors. In this module, we discuss various challenges of control design and validation for CAVs. Also, model predictive control, or MPC approach, is introduced to address some of these challenges. As a case study, designing an autonomous cruise control, or ACC, based on the MPC technique is also described in detail. First, please let me talk a little bit about my areas of expertise. I am the director of Smart Hybrid and Electric Vehicle Systems, or SHEVS laboratory at the University of Waterloo in Canada. I was recruited to Waterloo from the Vehicle Dynamics and Control Lab at the University of California, Berkeley, where I undertook my postdoctoral studies. My primary area of expertise is controls, along with optimization and artificial intelligence as secondary areas. I have worked extensively on developing control systems for automotive applications and partially for autonomous robots like drones. Over the last several years, as principal investigator, I have been leading a few collaborative research projects with a major car company totaling around $3 million, mainly in the area of vehicle control systems, including automated vehicle controllers. These projects have been financially supported partly by several governmental funding agencies in Canada. Now, please let me provide some background information with regard to AVs and CAVs. New technologies have made the development of onboard vehicle sensors with the lower cost possible. This, along with advances in embedded digital computing technologies, has significantly contributed to automated vehicles or AVs. AVs sense their surrounding environment using their onboard sensors such as radar, LiDAR, and camera. For example, radars can provide the intervehicular distance as well as the relative speed to the preceding vehicle. The information collected by the onboard sensors enables AVs to react to the changes in nearby traffic accordingly, with little or no input from the driver. By making proper decisions, particularly in emergency situations, automated driving technology can enhance the driving performance and safety. This is very important, particularly in emergency situations, as automated driving technology reduces the effect of error in human judgment, which is a major contributor to car accidents. As you probably know, many major auto and tech companies are currently working to develop automated driving technologies. The performance of AVs can be further improved by using a broader range of information about upcoming driving and road conditions. Recent cutting-edge advances in vehicle communication technologies enable the development of connected and automated vehicles or CAVs. For instance, using GPS and GIS variables such as position in route and road grade can be measured. Vehicle-to-vehicle or V2V communication provides information of surrounding vehicles' positions, speeds, and accelerations. Vehicle-to-infrastructure or V2I communication enables sensing traffic speeds and traffic light scheduling. All of these new pieces of information obtained through connectivity will enhance automated driving systems. The control systems are one of the key enabling technologies of CAVs. As shown in this slide, the information about the vehicle's surrounding environment and road that is collected and measured by vehicle navigation and communication systems is received by the control system for processing. Vehicle states are measured or estimated by the onboard sensors, and associated information such as inertial measurement unit or IMU data is sent to the controller as well. The controllers then process these pieces of information to determine appropriate braking, acceleration, and steering commands that are required for safe and smooth operation in different driving situations. In practice, design and validation of control systems that are suited for CAV applications remains a challenging task as discussed in this course. There are different challenges involved in designing and validating high-performance controllers for CAVs, and the following challenges are covered in this course. First, there are multiple objectives and constraints which should be taken into account in the CAV control design process. Some of these objectives are safety, comfort, and fuel energy efficiency. Examples of the constraints are the limits associated with the vehicle component's performance, for instance, maximum traction and brake forces available on the vehicle. Second, there are flaws in communications and sensing, which, along with the uncertainties in road conditions and variations in vehicle parameters, complicate the CAV control design. Packet loss, radar detection errors, vehicle mass variation, and road friction coefficient changes are examples of factors contributing to the uncertainties. Third, processing obtained data and information to calculate appropriate commands by the control system must be sufficiently fast to create responses in the time frame meeting real-time implementation criteria by considering control hardware computational power limits. As mentioned before, MPC approach is introduced in this module to address some of CAV control design challenges. MPC is a control design approach which has been used in a variety of applications and received a great deal of attention from the automotive industry in recent years. This method, as discussed in this module, is a good fit to CAV controls as well. There are different variants of the MPC approach which have been taken into account to solve control problems in AVs and CAVs. In this module, we introduce the conventional MPC approach along with its fundamentals, advantages, and disadvantages. In the MPC design process, the key elements that need to be specified include plant dynamics, objective function, and constraint on system state and output, and control action. As shown in this slide, within an MPC controller, a computationally efficient model of the plant, so-called control-oriented model, is employed. Using this model, the future behavior of the control system over a finite horizon can be predicted. At each time step, the predicted future states are used to formulate an optimization problem. This problem is solved, and the solution to it is the sequence of optimal control actions where the current system states are considered as initial conditions of the problem. This procedure turns the device control system into a feedback controller. Another challenge to develop proper CAV control system is associated with sensing and operational uncertainties. An MPC controller has some parameters, for instance, the weightings of the objective function or prediction horizon length. We can adjust these parameters to achieve a good performance in different scenarios, even when sensing errors and operational uncertainties affect the control system behavior. For this purpose, the controller parameters will be tuned using systematic, robust calibration optimization techniques, where the tuning is formulated as a high-level stochastic multi-objective optimization similar to robust design optimization techniques as shown in this slide. Autonomous Cruise Controller, also called Adaptive Cruise Controller or ACC, is an example of Advanced Driver Assistance Systems or ADAS. According to the SAE International intentional definition, these systems are considered as level 1 autonomy. ACCs improve road throughput, safety, comfort, and the ecological performance of the vehicle. The intervehicular distance and relative speed of preceding vehicles are provided to the controller by a radar, camera, or another device. Using this information, the control system adjusts the vehicle's speed to follow the preceding vehicle smoothly with a safe distance. For our case study, an MPC-based ACC controller is designed and evaluated for a typical pickup truck. Two different scenarios are considered and compared. In one scenario, it is assumed the vehicle is only equipped with a radar, while in the other one, the vehicle uses V2V communications in addition to the radar. The simulation results are compared to investigate the impact of V2V communications on the ACC performance. To define the control problem, a typical car following system is considered with the host vehicle and its preceding vehicle as shown here. The desired distance plus the distance error constitutes the distance between two vehicles, or L. The desired distance should be maintained by the device controller. The smaller delay of V2V communications and other factors improve the performance of ACC system with V2V communication, as discussed in this course. Now I conclude my presentation, and I hope it's helpful to provide some insight into the IEEE Autonomous Vehicle course, and I hand it over to Dr. Steve Wuzar.
Thank you, Dr. Lashkarian. So my my section that I'm going to be talking about is sensors for autonomous vehicles. And the objectives of my course are for people to understand the role of sensors in a self-driving car, have an understanding of typical sensors that are going to be found on an autonomous vehicle, and then really know a little bit more detail about the benefits and drawbacks associated with different sensing modalities. So I've broken this down into three basic topics. Number one is just the role of sensing in AVs, and then I talk in more detail about sensors for dead reckoning and inertial navigation, and then sensors for vehicle perception. So my background, so I have a bachelor's, a master's, and a PhD in mechanical engineering from the University of Michigan. My dissertation was on teleoperated mobile robots. So that is robots that humans operate without line of sight and are basically using them as tools. I went off to Johns Hopkins University and worked on a series of problems involving teleoperated satellite, on-orbit satellite servicing for NASA, and then moved back to Michigan, working on the University of Michigan and Ford's next generation self-driving car program in about 2015, 2016. My primary job at the University of Michigan was working on the vision sensor suite for Ford's self-driving car program, and then as well as helping with behavioral systems, control systems, mapping, localization, the entire full stack of self-driving systems. In 2017, some colleagues from the university and I spun out May Mobility. And at May Mobility, we are really focused on bringing self-driving technology to the streets today. With the technology that's available today, and not waiting for next-gen sensors, next-gen compute, next-gen communications, but really serving a transportation need in the near term. And our goal is to get out there and put people in the vehicles safely and eventually transform cities with autonomous technology. So at May, we are live in 4 cities, and we've carried over 100,000 riders in our vehicles. We are in Detroit, Michigan. We're in Grand Rapids, Michigan. We are in Columbus, Ohio, and we're in Providence, Rhode Island. And if any of the listeners here are located near Providence, Grand Rapids, or Columbus, those are public free shuttles. Anyone can go and hop in a shuttle. No NDAs required, no liability waivers. They can go and jump in those shuttles anytime. So I invite you to go check out some self-driving cars in the real world. So the first topic I'm going to talk about is the role of sensing in AVs. And, a self-driving car is a very complicated electromechanical device. In order for LeBron James here to sit back and relax and check his phone in a driverless vehicle, all of many different subsystems have to work together flawlessly in order to let that happen. And if you read the chart basically from left to right, we have dead reckoning, perception, and mapping are the beginning of the entire process. And so that is something that is very important. Dead reckoning and perception are feeding into localization, object tracking, which then feeds into the behavior, which is sort of what the car is going to do over the next 10, 15, 30 seconds, which then goes down to the low-level control, which is basically the brake, throttle, steer command, and then finally you get the actual actuation. So again, this is perception is basically and sensing is one of the very earliest parts of the feedback loop that happens for a self-driving car, and so it is of critical importance. So the second topic that we're talking about is sensors for dead reckoning and inertial navigation. And Self-driving cars need to know with high precision their position and orientation in the world. Now, human drivers don't actually need to do this. You probably need to know your position within a lane to about a foot, whereas you don't even necessarily need to know your longitudinal location with a precision of even a mile if you're on the highway and you don't really know where you are. But self-driving cars don't have all the context that humans have, and so typically they need to be localized to within an order of centimeters within their lane and also longitudinally. So there's a number of ways in which we can accomplish that, and typically there's two stages to finding this localization. The first is basically dead reckoning, wherein the vehicle uses inertial sensors to determine how far it should have gone if there was no disturbances and the sensors were extremely accurate. So that includes basically counting ticks of encoders. It involves checking your orientation with some sort of yaw angle sensor, and you basically have a good guess as to how far you've gone. Now, you're not always going to be right, so then what you want to do is you want to do some sort of loop closure or matching. So you use sensors that look at the outside world to confirm that you have indeed gone as far as you think you've gone. So you can imagine dead reckoning would be similar to closing your eyes, taking a few steps forward, and then opening your eyes. You probably had a pretty good idea of how far you traveled, but you could confirm that when you opened your eyes. High quality dead reckoning does reduce the requirements that loop closing has to do. If you have really good dead reckoning, then the adjustments that you have to make on your loop closure is much smaller, so you can get away with less compute there. And specifically to the end of dead reckoning and inertial navigation, I talk about encoders, inertial measurement units, and fiber optic gyros, as well as GPS, and the role of GPS in global positioning versus relative orientation and positioning. So finally, I talk about sensors for vehicle perception, and this is typically what people think of when they think of sensors for autonomous vehicles. The inertial measurements don't get some of the press and the glory that things like LiDAR and radar and cameras do. They're both very important, and they have extremely important functions in a self-driving car. And for vehicle perception, this is basically the vehicle's eyes and ears. So as I mentioned before, they're used for localization loop closure, but they're also used for obstacle tracking. So that's looking at static obstacles in the world like buildings or concrete barriers. It's also used for looking at other agents in the world such as cars, trucks, bicyclists, pedestrians. We can even use sensors for vehicle perception to read lane markers and ensure that we are in the correct lane or that we're centered in a lane. And in this topic, I cover sort of the main typical sensors that you have in a self-driving car. And they have different sensing modalities, and the reason you want to have that is because they each have their own strengths and weaknesses, and we want to layer them on top of one another so that if there is a particularly difficult situation for example, a radar to handle, then the LiDAR can come in and handle it, and vice versa with the different layers of optical, radio, sonar sensors. And finally, I talk about sensor fusion, which is the process of taking all of the different data sources and building up a really accurate picture of the world around you. It's not always obvious how to weight your radar sensors versus your LiDAR sensors, even different kinds of LiDAR sensors that may be on a vehicle. And so I spend a little bit of time talking about the role of sensor fusion for perception as well as some techniques. With that, I'm going to move back over to Ingrid, and we will open up the question and answer section of the webinar.
Thanks so much, Steve. I appreciate Alex and Nasser and your presentations. At this time, I just want to remind the audience, if you have questions, please make sure that you type them into the Q&A section. And now we will start with some of the questions that we have already been submitted with. This particular question is for Steve, so I'm going to just pose that to you. What do you think of the claim made by some industry insiders that LiDAR is a crutch?
Yeah, that's a great question. It's a really hot topic recently. You know, at May Mobility, our focus and you know, my true belief is that we need all the different sensing modalities to be able to deliver on the promise of self-driving cars in the near future. Is LiDAR a perfect technology? Absolutely not. Neither are cameras and neither are radar. And that's why we need to build up and layer these sensors on top of one another. The fact of the matter is that LiDAR gives you a really good, dense 3D point cloud view of the world around the vehicle, and in my opinion, despite the shortcomings of a lot of LiDAR sensors, it really is one of the best sensors that's out there, and it doesn't make sense for our perspective to, on principle alone, not use a sensor like that. You can't get that type of data from any other sensor that's available, and so, you know, while it's not perfect, it certainly is very, very useful. And until something can come in and replace it, I think it's going to be here to stay.
Thank you. Our next question is actually posed to Nasser. This question is, which CAV control techniques are covered in this course?
Thank you. We are talking mostly about model predictive control approach. This is a technique which has received a great deal of attention because for designing a control system for autonomous vehicle or connected and automated vehicles or CAVs, we have some different objective function, different constraint, and the beauty of the MPC control technique is that you can include in a systematic way all of these constraints and objectives. Therefore, we are covering this technique in the CAV control module.
Thank you. And this is a question to anyone on the panel. It's, can electromagnetic induction loop be used for detection of near objects in autonomous mobile with wireless? Does anyone want?
I'm trying to think that through.
Yeah.
I hear wireless and all of a sudden I pick up.
Yeah, so there are, I think that if I understand the question correctly, there are sort of induction loops already used in traffic today that's used for detecting if there is a car at a traffic light, for example. And it could be useful to self-driving cars or even just connected cars in general to be able to know that information. But if you've ever ridden a motorcycle and went to a timed light or a bicycle, you may know the pain of not being able to trip that induction sensor because you don't have enough iron or steel with the vehicle that you're using. So there are pitfalls with it. It's not foolproof. But yeah, that's a pretty typical sort of traffic sensor that's used. In the future, I think we probably will go away from that, if only because cameras and radar and LiDAR could also be deployed as infrastructure in the world and get more high-fidelity information about what road users may be present on the road and determine how vulnerable they may be.
Great, thanks, Steve. This one actually sounds like a sensors question for you as well. This one, will camera sensors replace all sensors?
I don't have a crystal ball, right? So I think that there is a possibility that in the very long term, we could get away with camera only for self-driving. I think you'd also have to have some inertial sensors. There's no way to get around that. But could it replace radar and LiDAR? Maybe. In the near term, definitely not. They're just the amount of data that comes from cameras is just so vast. It's very hard to separate out the salient pieces of information from sort of the background clutter, and it takes a lot of processing power. So there has to be significant advances in computing power and algorithms for computer vision for that to come to fruition. I also think that we have the potential to do better with self-driving cars than humans can do. For example, if it's pouring rain out or really foggy, the cameras are going to have the same pitfalls as human vision. And so I think it really does make sense to continue to use radar in that circumstance to be able to navigate in those types of scenarios.
Okay, great. Thank you. The next question we have is, how does deep learning work in the automation of the CAV, and which algorithm is the best in this aspect?
So I guess I'll try and take that one. So I mean, the thing is that there's going to be a lot of different sensor modalities that are going to be on the platform, and what's important is the ability to make decisions on the fly, right? And so like as a result, like you could have an automated process where it's like, oh, I have this car this far away, I'm picking it up on this vision system, therefore I need to slow down to this speed. But those types of systems tend to be somewhat brittle. So on the other hand, if you use let's say a deep learning approach, and again, like there's going to be issues in terms of the practicality of that implementation, in terms of how do you train it, did you cover all the edge cases, and the like. What you're trying to do is you're trying to kind of, as the vehicle goes along and experiences more of its environment around it, more scenarios, things that it was not initially programmed to do, but eventually will learn it. It actually you would be able to handle those scenarios as well, and then take things like from the vision system, the LiDAR system, the radar system, probably other information, very importantly like wireless information from other platforms, in order to make informed decisions. So I think that, like in terms of like deep learning, I think I think there are several approaches that could be used. I think the jury's still out, but I think one critical element which should not be underestimated is also like processing power as well, like being able to not only because the more information sources you have, the more processing you're going to do, and you also need to do it in near real time, like almost as fast as a human being. Otherwise, the platform becomes slightly dangerous.
Thank you, Alex. All right, we have a few more questions to cover, which is awesome. Thank you for all of the participants submitting questions. The next one, how advanced is CAV technology among car makers, jurisdictionally, Europe, North America, China, Korea, India, Japan?
I think what you're seeing is a really interesting landscape here with changing alliances between auto manufacturers, suppliers, tier one suppliers, and startups. So I'll give. I don't know who's sort of winning. I think that sort of the jury's still out. A lot of people have made promises about when they're going to have robotaxi services. Many have said the 2021 timeframe. Some people have said a little bit earlier. Some people have said a little bit later. One example I want to give is sort of Argo. This is a startup that was heavily invested in by Ford. Ford had its own AV team, and they still do a lot of work on AVs, but they've basically ceded a lot of the software side to Argo. And then just recently, VW came in and made a significant investment in Argo as well. And so they're going to sort of share some of the learnings and some of the software from Argo. And so I think what we're seeing is it's a really, really hard problem, and even the global automakers are having to share resources to tackle this really, really difficult issue. And it's not clear who's going to win. And I think that's why a part of the reason why it's such an intriguing space is that there is so much white space and there is so much opportunity for for advancement, and why you never know if it's going to be who's going to be the next Mobileye, who's going to be the next Argo.
Thanks, Steve. Another question, what kind of backup controls are in place for the vehicle control function in case of a failure in a component?
You know, it typically depends on what you're talking about. There are sort of critical elements like brakes and steering that you need to have double or even triple redundancies on. This is where sort of your failure modes, effects, and analysis comes into play, and ISO 26262. You know, standards about what is acceptable in terms of safety and how to design robust, safe systems. Any self-driving car system is going to have you know, backup safety system. Now, what that backup system does, you know, depends on the use case. If you're in a low-speed sort of factory environment, it may be the safest thing to do to stop if you have a backup, if you have a problem and you need to back up. However, if you're on the highway, it doesn't make sense to just slam on the brakes. And so there's also this notion of safety of the intended function, or SOTIF, which there's a new standard out in the last 6 months. It's less of a standard and more of a guideline, but really it depends on your operational design domain and what it is you're doing, what those backup mitigations and fail operational modes should be.
Thanks, Steve. The next question is, with the autonomous vehicle technologies, do you feel that currently this is constrained to specific use cases for traffic, highways, and typical roads? What about situations where the car cannot see a cyclist that is crossing the street or a pedestrian just out of nowhere crosses the road?
I mean, the thing is that autonomous vehicles, you know, these platforms, like it needs to be. Well, I think that going back to the question about the deep learning, right? Like autonomous vehicles, just like human operators, you know, you're essentially what you're doing is you're replacing the human operator with the vehicle itself, like even depending on what level of autonomy it has, right? So it needs to be prepared for, you know, the unknown, right? So like the pedestrian walking out, or the cyclist, or let's say some animal that goes out on the road. Like, you know, how do you train an autonomous vehicle to be able to perform in an environment like that? So one thing is that of course you're going to have to, you know, the key thing is to try and train as much as possible within a controlled environment before you put that platform out onto the road. So now the question is, how does the experience of that platform or that autonomous vehicle be able to operate, and then all of a sudden something that never encountered before or never was initially trained with, be able to react in a specific way? So, you know, so let's say looking from sort of a theoretical sort of perspective, or, you know, like what would folks do? And one thing is, could you, for one, exchange experiences between autonomous vehicles? Right, so that, again, that connectivity element comes into play. So maybe one autonomous vehicle has encountered, let's say, construction in a downtown urban area, and perhaps a whole bunch of other autonomous vehicles that are operating in that same city never saw what a traffic cone looked like. Or you're driving and all of a sudden there's like a herd of deer that are crossing roads, which, you know, in New England is not an uncommon sight, but let's suppose that there's an autonomous vehicle in another part of the country here that doesn't know what deer is and all of a sudden encounters one. I think there needs to be at some point some sort of like exchange of experiences that further help the sort of training of these vehicles. So not done in isolation, but you know, and the reason is that when it comes down to it, like, you know, these vehicles are going to be sort of first in line that have to act, like, you know, in a split second, what is happening in front of it, right? So, you know, just like if you're driving along, like you've never probably seen a deer before, let's suppose like you're a new driver, and all of a sudden this animal comes out. you need to react in that split second what that's about. But you probably have heard from other friends and family, like, this is like, beware of deer, this is what it looks like and might come out on the road. I think there needs to be some sort of sharing of experiences that would help that sort of machine learning, that artificial intelligence on these platforms to make the right decisions. Otherwise, if it doesn't, then the safety factor that we're trying to go after with respect to these platforms begins to diminish that reward.
I just want to add one more thing, that connectivity also can help. I mean, I have heard some arguments that to implement fully autonomous vehicles, the connectivity technology like vehicle to vehicle, even vehicle to passenger, vehicle to cloud communication should be in place, because if there is a vehicle that can see an object or something going on that the other vehicle cannot see, this information can be shared with the other vehicle that don't have that sort of information. Therefore, adding connectivity to automation can provide a lot of information that can help to implement autonomous vehicle in situations that are multiple participants, there are very complex situations.
Exactly.
Thanks, Nasser and Alex. The next question, what's the best sensing method you found which localizes a vehicle to be plus or minus 10 centimeters, not including LiDAR or computer vision techniques?
Well, that's not fair. Those are the best ones. Not including LiDAR or computer vision. I mean, you're really putting your hand behind your back here. There's a type of consumer grade GPS will not get you plus or minus 10 centimeters. It's what's in your phone, and it's going to get you plus or minus 1 to 3 meters. However, there are technologies like RTK GPS and DGPS, which basically have a correction factor that account for aspects like atmospheric effects that are local to you and your location, and that can get you plus or minus certainly 10 centimeters, if not 5 or fewer centimeters. Now, the problem with GPS is that it can be easily jammed. So actually, you can buy don't do this, but you can go and you can buy a GPS signal jammer, and then you are in trouble if somebody does that. And also, it's subject to multipath. And so, even though the precision in most cases is high, when you get into an urban canyon type environment, it does tend to have some issues. So that's why you want to have redundancy in your localization as well as in your perception. But if you only want to have one localization methodology and you really want to get within 10 centimeters and you don't want to use LiDAR, I'd say you should use some kind of corrected GPS.
Yeah, and maybe just to add to that also is it's actually kind of a well-timed question, because I actually have an upcoming conference paper at IEEE Global SIP in Ottawa that actually talks about alternative methods for doing localization at that resolution. And and one approach which you can do is you can always use sort of passive listening of different types of wireless emissions. Like, let's say if you don't want to go to GPS route, and then through data fusion you can actually also extract that type of localization. So, and this is a technique that's actually been looked at for like the past, 50, 60 years by, national defense applications where you're trying to localize wireless emissions. But the same sort of technology could also be used for locating vehicles with that sort of resolution.
Thanks, Alex and Steve. We have just a few more minutes for a couple more questions. This one is, what is the control-oriented model? Is it data-drive statistic model or simplified physics model? What is the key factors, or what are the key factors to tune the model?
Yeah, I can take that question. Control-oriented model is at the heart of our model-based controller like model predictive control. It could be data-driven or could be physics-based, but eventually the parameters of this model should be tuned such that it has very close to the plant model, to the real vehicle model with 5%, 10% difference. Therefore, it should be accurate and at the same time should be very simple because our MPC controller needs to do an optimization based on this model to find the best actuation. Therefore, it could be both physics-based or data-driven as far as it's close to the real vehicle and is computationally simple.
Thank you. So for our last question, I'd like to pose this to each of our presenters today. This is from a PhD student who would like to go deep into the field of autonomous vehicles. How would you give advice to how to go about this? Let's start with Alex, please.
Oh, okay. No pressure. I mean, the thing is, first of all, you have to sort of, there's a lot of different rich areas that one can sort of pursue, a dissertation topic, right? So you can do everything, from a sensor's perspective, and you can really go deep into things like, for instance, if that's your thing. So, for instance, vision and LiDAR and radar and maybe different other sorts of sensor modalities. So those individual technologies, unless you go into device physics and stuff, are either extensively well studied, or in the case of LiDAR, is right now actively being researched, but maybe in a few years will mature. Sort of one really key dissertation topic would be how do you fuse that data together, and that data is really tricky because there's different sampling rates, there's different quality of the type of data that you're getting from each one of those sensors. Some of that information might be wrong, you might not get the complete picture. So that by itself could probably spin out several dissertation topics. So you might want to start with some of the low-hanging fruit, let's say take two, and then really try and see how that would work in terms of, fusing those types of data together and then compare it against an established benchmark. Another topic, and I think this is what Steve mentioned, which is excellent, the idea of jamming GPS, that is a very scary topic people don't talk much about, which is autonomous vehicle security. And that's actually something that, in the Vehicular Technology Society, we have a group of folks in our community that actually look explicitly at automotive cybersecurity. And imagine now something that's completely autonomous being hacked. Imagine you have this level 5 autonomous vehicle, it's driving on its own, and then all of a sudden you're not in control, obviously, but this thing is doing not what you're supposed to. Somebody else has taken over your vehicle. It's already scary enough that human-operated vehicles are being hacked, but now an autonomous vehicle. So that also, if you're into the security world, would be a area ripe with great opportunities for dissertation topics. And then lastly, of course, I'm biased, connectivity. We have not, the community's still out there in terms of what is a solution for connectivity. Is it V2V? Is it V to roadside units? Is it 5G, 6G? Even light communications. People have looking at the lights, tail lights and headlights between vehicles to communicate information. No one's really come down to what are kind of the winning technology or a hybrid solution of these wireless technologies that would facilitate the exchange of information. And there's a lot of challenges associated there. So I mean, just off the top of my head, those are kind of sort of a few great dissertation topics that even some of my PhD students right now are working on, but no doubt there's the entire community is really interested in finding solutions to those challenges.
Thanks, Alex. Nasser or Steve, any last words before we close the webinar today?
I just can.
Sure. Go ahead.
Do you want to talk, Steve? Just about doing some PhD research in autonomous vehicles, I think there are great opportunities because there are big challenges. I'm talking in terms of the decision making and control systems. When we have multiple vehicle situations like intersections, roundabouts, and we have human-driven vehicles, you have your autonomous vehicle, decision making becomes a very complex task because, you don't know what the human driver is going. Even for people, when they want to merge in a roundabout or intersection is difficult. And of course, artificial intelligence as emerging field, there are many methods like, reinforcement learning, deep reinforcement learning. They can be combined with some model-based techniques like model predictive control that I have discussed in one of these modules to come up with a good solution. But in the area of decision making and controls of AVs or CAVs, connected automated vehicles, there are still a lot of challenges to come up with technologies which are reliable for real world conditions that can be considered as a PhD research.
I'll keep mine short and sweet. What I look for when I'm hiring a roboticist is someone who's done some work in the real world. So simulation is great. It's got its place. Using existing data sets is great. It's got its place. But what I'm really looking for is someone who's gone and implemented something and gotten dirty and found all the problems that happen with deploying it in the real world, because it never works the way that you think it's going to work. And that resilience and that experience of troubleshooting in the field is something that we look for. And it's really, really valuable for folks who want to get into this industry.
Thank you. At this time, we invite you to learn more about the IEEE Guide to Autonomous Vehicles. Please see the links noted within the presentation, as well as the resource list within the platform. I'd like to thank you all for your time, and a big thanks to our presenters, Dr. Alex Wislinski, Dr. Nasser Lashgarian Azad, and Dr. Steve Vozar. I want to wish you all a wonderful day.